from, I think, Singapore and Sydney, in that order, to come down here and give the second part of a talk. In October 2021, Joe Hayes presented a Zoom session which was entitled From Stradivarius to Speaker, Technology for Improvements in Sound Delivery and Room Acoustics Treatment. Interesting concept, putting those two things together. This outlined his patent applied for DAS AuReality technology to us. For those who missed this, I'd certainly suggest you go and have a bit of a look back on our AES Melbourne website, because there is a summary of it there. It's not the full thing, but there's a summary there. This is the second session for Joe. In this session, Joe will briefly summarise the background and developments leading to his DAS AuReality and some of the implementation challenges and successes along the way. But the exciting bit is now that we're here, he will demonstrate this technology to us. My view is that audio demonstrations are like perfumes, food and sculpture. It does not work over Zoom, you've got to be there. Okay. We are well familiar with a good concert hall having clarity of performance and a balanced enveloping sound field without hard echoes. We seek to capture this in our recording and listening experiences, but we must often put up with less than ideal acoustic listening environments. DAS AuReality technology tonight tackles this. The direct sound is preserved, but rather than remove information destined for uncontrolled auditorium and listening room reflections, DAS AuReality creates an ideally balanced reverberant field prior to the intervention of the room acoustics at the speaker. And so, without hard echoes and associated distractors. This room is probably not ideal for this technology because this room is acoustically treated. It would be better if we put some sheets of glass on all the surfaces, wouldn't it, Joe? It'd be more.
Well, you get pretty well the same sound no matter what's it.
Yeah, because that would give a better demonstration. But here, because it's acoustic treatment and it's quite dry, you'll probably find that you have to use all your listening skills, and that's good. Joe Hayes is Sydney-based, I mentioned that. He's a musician and inventor. He understands musical acoustic delivery. Joe's exploited his knowledge of physics, mathematics and psychoacoustics to make breakthroughs in audio playback technology, leading to the development of the principles of diffusion at source, or DAS. Joe has had decades of experience designing and manufacturing innovative products for musicians, and I hope I get all this right, such as his PASAC, MIDI, Sentient 6, Unity 8 mixer and EC1 equaliser preamps. Also teaming with Larry Fishman and Martin Guitars, amongst others, for the world market. Tonight I'd like you to welcome Joe to this evening, and I'm sure you'll get a very enjoyable and informative experience from him. So thank you very much, Joe.
Thank you, Graham. So first I'm going to recap in a brief form the paper I gave last October. I've called it As You Go Along. The best part of being an inventor is coming up with a name for things. and as I'm moving more into this, I've just got omnidirectional acoustic treatment. And you get this from these phase array of drivers. You can do it any frequency band you want. Whatever frequency band you do it is good to do it in, but the low-lying fruit is a tweeter, because a lot of the psychoacoustic, your consonants are 1 to 4K, and if you can get that sorted, it's very, it's bang for your buck. And because it comes back to the bill of materials, this platform, the array platform, is what we'll demonstrate tonight. Where we came from is this, the reflector technology, where we have a 2-inch aluminium driver. And what I worked out with this, I'm quite proud of this, I worked out how to point source focus that to 38 millimeters away where the acoustic center of the driver is. And what I'm saying is you may see these diffusers on walls in studios. I will go out on a limb and say that none of them work, because if you understood Schroeder's original work, it assumed a planar wave hit it. Now, if you're here making a noise and it's on the wall It's not a planar wave that hits it, so they all don't work. And I proved that, understood the maths enough to do this, and heard this straight up. I'll play that later, and knew that there was something going on here with this technology. So, in the recap, the 30 years ago I come with the word omni-diffuse, and now I think it's actually quite appropriate word for this. So, we've got these in walnut and bird's eye maple here. These are the measurements, and this is the polar measurements. Stack of lines, they're all on top of each other. The scale is 10 dB. You see, they're in a narrow band of 4 or 5 dB, and until you get way up to the top end. And as described by these diffusers, there's a plate frequency here and a plate frequency here where it becomes a normal driver for a very small angle. But for an omnidirectional loudspeaker, I showed it to someone in the industry professionally recently, and they said, not a bad set of curves. The set of curves for these are even better. So, okay, we've got a way now to make omnidirectional speakers, because if you know the MBL speakers, they're not cheap. So here's a low-cost method to create omnidirectional sound. There is something different, though. So I'd say those curves are good to 10K. And a lot of sound engineers will say if you can get the sound right to 8K, you've pretty well got it covered, And that light blue area is where we're diffusing. And what that means is we've removed the specular reflections out of the room. So if you're a studio builder, this is helpful because I've heard in the film industry, people are given the sound files to a film and the broom closet, and they say, mix this in 3 weeks. So there is no studio, you just got to work somewhere. So it's good for creating a space that's accurate without the cost of acoustical consultancy. I'd like to say this room, I think, I saw it and I got, oh no. But then, having spent the afternoon with it, it's a really good room. So whoever did these acoustics, it's not over-absorbent, it's very flat, you can hear me fine. So unless they're amplifying my voice somehow, it's a pretty well done room. But there are not many people around who can do this and do it properly. All right, so that's this model, the measurements. And a little twitch there is, the interesting thing about the sound fields, I want to note that the person who modelled this on ComSol is sitting in the audience tonight, Toby Gifford. He's a national treasure, and I'll talk about that a little bit more later on. But essentially, once you see this, once there's a step response, to use a signal processing language, in the recorded audio, the sound field in the room will move in concert with the audio's cues, not with this room's cues. So let's look at this AS8. There's its set of curves. Again, pretty nice. And that's around the polar. They're going out to 12, 13K. There's the same diffuse band. And they've got the same phenomena of this twitching. It took us a long time to work out why these speakers sound like they do. And in reverse, once you understand all this, you learn a lot about psychoacoustics and what isn't and isn't important and what is probably going on. I've been able to resolve this because I studied the Masters of Architectural Acoustics with Anita Lawrence. So I'm trained as an auditorium designer, and we went deep into psychoacoustics in that coursework Masters. So that's where I picked up a lot of the knowledge. I did electronic engineering undergraduate, and the two weren't agreeing with each other very much. Okay, so what I'm doing here is focusing in on the ComSol modelling. On this side, we just chose 3 frequencies, 9, 11, and 15K. Why? Because the plate frequency is 13K. I wanted to see either side of the plate frequency. And we've got other MATLAB models and whatever. And what I can tell you is that this spinning motion you see here actually goes in the opposite direction when you get above the plate frequencies. So there's a whole, and it happens because, let's just get into some of this. So time correlated is the pebble in the pond. Perfect, perfect rings of energy because the explosion happens in unison, in the same in all directions. Generally, that's their science, right? The perfect point source, and that's what they're striving to do. Now, this is Toby's modelling here. I asked him to model 5K at 1 metre, and these are the intensity vectors. COMSOL's great. I think you had their COMSOL to change something, didn't you, with COMSOL to get the intensity vectors. So these are the direction of, these are particle velocity vectors. So it's like current in electron engineering. Sound pressure level is just the voltage. That over there is sound pressure level curves. So one thing we noticed is that there's no, what we call this radial motion or tangential motion. If you put a normal piston radiator on, these things will be swirling when you start attenuating or focuses. So these all point back to a point source. And when you think about it, they have to, because if there is effectively no energy going this way, because if there was, the law of physics wouldn't permit that rate of spin happening there. So it's all very much a point source technology, but it's got a time delay at the source. And that time delay is the diffusion, or diffusion at source, as we call it. So there's 1 metre 5 kilohertz, and as I say, once you go above the plate frequency, and you'll see the bending in different directions there, it spins the other way, and spins quicker. That seems to be a 90 degrees phase, and I've done that by just watching these. There seems to be, if you're looking at the speed of this rotation and with the actual excitation, that's a 90 degrees lag from in front. When you go up to the plate frequency, it looks like 270 degrees. So it's a quicker rotation. So, and that's why we chose these 3 frequencies, 2 within one mode and the other in the next mode. It's from this motion we got this rotosonic logo. If you look carefully in the back of these speakers, we use them as air vents, that little symbol, but it's, okay, we're rotating time. That's essentially what's going on here. Then we look at what does this look like in sound pressure level? So we've got Toby to model sound pressure level. That's a 1 wavelength at 5K at half a metre. And when you've got a velocity quiver that's doing this, particle velocity, it looks like that in sound pressure level. It's a bent wavefront. Now, the eccentricity, which is the non-circularity, seems to be 90 degrees out of phase here, but because it's connected to wavelength, as soon as you change frequency, you change the wavelength, you change the shape of the elliptical sound pressure field. So, as Toby first used the word, it looks like it's shimmering when we first had the monitor. So this sound source, it's a point source, but it shimmers because it's got the thing that the variable in these equations is time. It actually has, and that's what Schroeder said, you get the Fourier coefficients are equal in all directions, equal power in all directions. The thing that gives is time, and there's actually a time delay at the source depending on what angle you're on. For me, from a musical instrument point of view, someone was here today and he talked about how this sounded reminded of musical instruments, and for me it was the Martin guitar thing. If you're sitting around a Martin guitar, you don't have to sit 1 metre on axis. You'd be anywhere in the room and it sounds fantastic. And it's pumping out sound in all sorts of directions. And a lot of the sound may come to you from a reflected path, not even a direct path. But that's reality. A piston radiator is not a real sound. It's a man-made sound, and we all know what it sounds like. So the thing with the piston loudspeaker too is it's very hard to echolocate this, right? Because the echolocation is about a clear repetition of a direct signal after a period of time. But you'll see that in the next slide coming up. But you can see the bending wavefronts. You can see there's those 3 frequencies are all bent and mutated through here. So it's creating the sound field that is. It's wave packet, it's non-dispersive, it has the same shape and it travels out with just getting lower in level but not changing the shape of the transient that you get. And so you can see that with this pattern here, goes out in that direction. Depending on where you are, you're going to be in different parts of this, but as soon as you change the phase on one of those frequencies, this all moves. This becomes totally different. So without changing the spectrum, we've got a queuing system happening within the listening room of the audio recording temporal cues. or in my training, difference Lehmans, which is a psychoacoustic term of perceptible differences. So, the gentleman here earlier was the person who came up with the deterministic stochastic. So essentially, no matter where you are, your direct sound, the phase time delay across your ears is not great, not significant. So you get your direct sound here. And then psychoacoustically, and I don't know the mechanism, Toby and I discussed this a lot, the 7 rows of hairs on the basal membrane, is how is it done, but what seems that if you just get minutest subliminal repeat of a signal, that says that's an early reflection, and it just has a very derogatory effect on sound. So there is no way, given that every frequency at any angle is completely different from a direct sound, that you're going to get a repeat from the room in this. So you're essentially diffusing up the room and creating an energy in the room that is like the sound in the live recording, the reverberant sound. There is a distance where you get to the near field in an auditorium acoustics, or you just get the reflected energy from that performance. So I'd say that steady state sound is it gives you the reflected energy of the actual live room, and then the temporal cues are marked by this bending idiosyncrasy, and that's what you need for hearing, right? All you need really is your temporal cue markers and a flat spectrum that's free of reflected specular reflections, and that's what this is doing. So when you get a small change in the signal, that should be IID. I should fix that typo at some stage. This thing will rotate. So let's look at this. This is from earlier work. This is a MATLAB tool we wrote, where I've got same lounge room, a pair of Rogers speakers on this side, Rogers monitors, and these little reflector speakers on this side. Put in the same location, didn't touch the microphone, didn't change anything to the room. So you can see, and this is a correlogram in MATLAB. It's used to find energy. It's measuring correlation against the Morley wavelet. Without getting too details about wavelets are complex. You either understand them or you don't. So I'll just leave it at that. But it's correlating that, and when it's high correlation, you get whiteness. And this is frequency, bass down the high frequency, and this is time. So there's the direct sound, 0, and then at 95 centimetres and 160 centimetres, you can see the clear reflections coming back from the room. I change time to distance because it's just, I find it a better way to think about things. What is 10 microseconds? I don't know, how many millimetres is that? Don't understand. So we've got rid of the specular reflections with these. So that's really good news from an auditorium acoustician's point of view. I honestly wouldn't have thought that would have been possible, but if it wasn't for this shimmering time source, it now becomes possible. So again, on this side, because of the lack of room reflections, you're going to see the Mona Lisa, the original, and on this side, which is pretty well every room that we know with a normal speaker in it, you're going to get this Mona Lisa, which is a pretty good semblance to the original, but it's not quite the original, right? So, and I use the word subliminal. It is all very subliminal, this first 50 milliseconds in sound. Now, this is what's evolved since I gave the talk. Having built these, I've got to give you a bit of an apology in advance. It looks like we may have damaged the tweeter on this side earlier today with playing something through it too loud. That's because there's 50 watt amps driving 3 watt speakers, and I haven't put any protection systems in yet because I'm not the author of the electronics. But we'll listen past that. So this is what this technology needs to do next. I'm blown. So 3 watts RMS per driver, 2 are in series, or 2 might be in parallel. The other mistake I made with this is putting the drivers in series, because if there's a manufacturing variation on one, it gets amplified into the other from a voltage divider point of view. So next one, they'll be in parallel, and they'll get exactly the same electromotive force. But this is a 13 watt RMS, high quality amp. That's its circuit board footprint, 1.78 millimetres by 2.49 millimetres. 13 watts RMS. So these little squares here are the amps. That's how big they are, the scale. So ideally, and we are talking to the company that supplies these drivers, and there's lots of those sorts of drivers around, how to make a module, how to make an omnidirectional acoustical treatment tweeter module. If you build loudspeakers, you buy the thing, it's already flat. We put a crossover in it somehow. These are using LR4 crossovers, flipped product. They're normal loudspeakers in every way. And crossing it over, you give it a DC voltage, which is what they'll run on. These amps here, 200 watts RMS runs on 24 volts DC power packs. So it's a regulatory free space, which is good news too. Give it DC, you give it an I2S, which is your stereo left-right signal. And we have some DSP on here, which will do our algorithms to the amps, which is I2S. You talk to these amps through I2S. And do the crossover. And this little module you put whatever facade you want on it. And that opens up this whole world to the whole high-end market. When once you hear it, you see why that might be of interest to them. The problem with that, there's 1,000 manufacturers making 1,000 speakers each. It's a very diffuse market. But the lower profile version up the top here is good for a soundbar where you don't height's the big thing. We've got a Sonos Arc, it's 8.5 centimeters high. If you get above that, you start covering the bottom of the TV. So whatever you do has got to be low profile. Or this version is this is how we've sort of done this. But what we've done here is we've got the amps in the back and we use 8 wires to take the 4 channels amplification through to the tweeter at the front. So that's it. It's not particularly complex, So that's what we're work towards, making them available, because then you can just buy the module and stick it into whatever system you want. And the bass amps are so small, we're even thinking that a bass amp on piggyback to the back of this would give you everything you need to make an active speaker all through that one hole. All you got to do is get the power in through the R7B connector on the back. So they're the self-contained flat response omnidirectional tweeter that also happen to treat the room acoustics. So that's a short summary. We'll get into some listening. Ms. Yates.
Anyway, thank you all for attending tonight, and we'll continue the discussion, which seems to be quite useful. Can you all please thank Joe for taking the time and coming down here and doing this